Welcome back. In the previous session, we discussed the thermodynamic functions of a closed system. Now, we can discuss some properties of an open system. A system in which the number of moles varies is called an open system. The internal energy function U depends upon the thermodynamic variables volume and entropy. But for an open system, the internal energy function U is a function of the number of moles N1, N2, N3, etc. Nn of n different substances. So, the state function we can expand U as du of V comma S comma n. Here V represent volume, S represent entropy and number of moles of the open system is equal to dou u by dou V at constant entropy and number of moles into dV plus dou u by dou S at constant volume and number of moles into ds plus dou u by dou N1 at constant volume and entropy and number of moles into dN1 plus etc. dou u by dou Nn at constant volume, entropy and number of moles into dNn. Here the change in internal energy with respect to the number of moles of the system at constant volume and entropy is given as the chemical potential for the open system, and it is denoted by the letter mu J. Thus, the internal energy for an open system can be written as du is equal to minus P dV minus T ds plus summation of J is equal to 1 up to n mu J dNj. Here this term comes for the open system. Then reversible chemical work delta Wc is equal to summation of J is equal to 1 up to n mu J dNj, and this term is the chemical potential involving term and it is known as reversible chemical work and it is an intensive quantity. Next, the legendary transformation of the above equation leads to dH is equal to Tds plus Vdp plus summation of J is equal to 1 up to n mu J dNj. Then dF is equal to minus S dt minus P dV plus summation of J is equal to 1 up to n mu J dNj. Then dG is equal to minus S dt plus Vdp plus summation of J is equal to 1 up to n mu J dNj. Here these three terms are extra. Here these terms dH, dF, dG as already we discussed, and here these three terms comes from the open system, properties of an open system. Next, in terms of Gibbs function, the chemical potential can be written as from the previous expression. Here dG is equal to minus S dt plus Vdp plus summation of J is equal to 1 up to n mu J dNj. When temperature remains constant, this term becomes 0. When pressure remains constant, this term becomes 0. So, for an isothermal isobaric process, the chemical potential can be written as dou G by dou Nj when pressure and temperature remains constant. So, the chemical potentials are equal for two open systems in equilibrium. It can be written as mu 1 of 1 is equal to mu 1 of 2. Here 1 and 2 represent two systems which are in thermal equilibrium. Here when two systems are in thermal equilibrium, the chemical potentials are equal. So, the chemical potential expresses a driving force for the flow of matter. Now, we can discuss some of the applications of thermodynamics. Here first, the black body radiation. Only the quantum theory of light can explain its origin. By definition, a black body is one which absorbs all the radiations it receives regardless of frequency. Spectrum of a black body has its peak at a higher frequency than the peak in the spectrum of a cooler one. The best practical realization is an isothermal cavity with a small aperture through which the radiation from outside may be admitted. In order to explain the black body spectrum, consider the radiation inside a cavity of absolute temperature T whose walls are perfect reflectors to be a series of standing electromagnetic waves. The spectrum of radiation being characterized by a function u of nu, where u of nu d nu is the energy per unit volume of the cavity contributed by radiation with frequencies between nu and nu plus d nu. Here u of nu d nu represent the energy per unit volume of the cavity between the frequency limit nu and nu plus d nu. Next, the number of independent standing waves g of nu d nu in the frequency interval between nu and nu plus d nu per unit volume in the cavity is found to be density of standing waves in a cavity is represented as g of nu d nu is equal to 8 pi nu square d nu divided by c cube. Here c represent the velocity of light 3 into 10 raised to 8 meter per second. Then according to the theorem of equipartition of energy, the average energy per degree of freedom of an entity that is a member of a system of such entities in thermal equilibrium at temperature T is half kT. Here K represent the Boltzmann's constant. The classical average energy per standing wave is given as epsilon is equal to kT. Here the classical average energy per standing wave is given by multiplying the above equation half kT into 2. Here 2 represent the degrees of freedom of the gas. Then we get it is equal to kT. Then u of nu d nu per unit volume in the cavity in the frequency interval from nu to nu plus d nu is given by the equation this classical average energy into density of standing wave, that is epsilon into g of nu d nu. Here epsilon is given as kT. Here from the equation 8 pi kT into here g of nu d nu is equal to 8 pi nu square d nu divided by c cube into epsilon into kT is equal to 8 pi kT nu square d nu by c cube. And this equation is known as Rayleigh Jeans formula. The radiation rate is proportional to this energy density for frequencies between nu and nu plus d nu. That is, the radiation rate is proportional to this energy density. Radiation rate is proportional, and from the equation it is clear that as the frequency increases towards the ultraviolet end of the spectrum, the energy density increases as nu square. Energy density increases as nu square. And this is the spectral distribution of a black body. Here in the x axis wavelength is drawn and the y axis energy density is drawn, and here it is the various temperature. At various temperature the graph will be shown here, and this represent according to theory, classical theory, and it is represented by an experimentally represented figure. In the limit of infinitely high frequency, u of nu d nu should also go to infinity, but in reality the radiation rate falls to 0 as nu tends to infinity. As frequency tends to infinity, in reality it is found that the radiation rate falls to 0, and this discrepancy is known as ultraviolet catastrophe. Next, Stefan-Boltzmann law. The amount of energy E lost by a body per second is proportional to the fourth power of its absolute temperature T. That is, E is proportional to T raised to 4. Fourth power of absolute temperature T. So, here a constant came, E is equal to sigma T raised to 4, and sigma is called the Stefan's constant, and it is also known as Stefan's fourth power law. Next, the Wein's law distribution of Wein's law, which is the distribution of energy in a black body spectrum. Stefan's law actually deals with the total amount of heat radiation comprising all wavelengths from a black body at a given temperature. It says nothing about the distribution of this energy among different wavelengths at different temperature. So, according to Wein's displacement law, for a black body, the wavelength lambda m, for which the emissive power E lambda has its maximum value, is inversely proportional to its absolute temperature T. That is, lambda m is inversely proportional to its absolute temperature T. That is, lambda m into T is a constant, and this constant is given as 2.93 into 10 raised to minus 3 meter degree. With a rise in temperature of the black body, the maximum intensity of radiation emitted by it gets shifted or displaced towards the shorter wavelength. Hence, the name displacement law. From the previous figure, it is very much clear. In the lower wavelength, the spectrum shift. As temperature increases, the spectrum shift towards the shorter wavelength. Here the 5000 Kelvin, it's shift towards 0.5. It shift towards shorter wavelength. So, Wein's displacement law is clear from this figure. Next, according to Wein's law, energy should be finite at temperature tends to infinity, which is in contradiction to Stefan's law. Similarly, Rayleigh Jeans law would not give a maximum, and the total radiation at all temperature is infinite. The failure of both Wein's and Rayleigh Jeans laws of radiation to fit the actual energy distribution curves showed that they did not choose a correct form for the function f of lambda t. So, a general law of radiation is required. Here comes the Planck's radiation law. In 1900, Planck obtained an empirical formula which agreed very well with the experimental curve. The oscillators in the cavity walls could not have a continuous distribution of possible energies, but must have only the specific energies. So, the oscillator energies is given as En is equal to NH nu. Here N stands for 1, 2, 3, 4, etc. So, specific energies are required. Then actual average energy per standing wave epsilon is given as h nu divided by e raised to h nu by kt minus 1. So, instead of kt, here comes h nu divided by e raised to h nu by kt minus 1 is the actual average energy per standing wave. This average energy leads to a Planck radiation formula, and it is given as u of nu d nu is equal to 8 pi h nu cube into d nu divided by c cube into e raised to h nu by kt minus 1. That is actually the Planck radiation formula. U of nu d nu is equal to epsilon g of nu d nu. Here g of nu d nu is equal to 8 pi nu square d nu divided by c cube. Here epsilon, instead of kt, epsilon comes h nu divided by e raised to h nu by kt minus 1. H nu into nu square gives h nu cube. Then 8 pi h nu cube d nu divided by c cube divided by e raised to h nu by kt minus 1. So, At high frequencies, when h nu is very much greater than kt, the expression becomes e raised to h nu by kt tends to infinity, which means that u of nu d nu tends to 0. That is, this tends to infinity means this is become 0. So, it is as observed. So, there will not be any ultraviolet catastrophe. At low frequencies, where the Rayleigh Jeans formula is a good approximation to the data. At low frequencies, h nu is very much less than kt. Here h nu by kt is very much less than 1. So, the equation 1 by e raised to h nu by kt minus 1 is equal to kt by h nu. Substituting this kt by h nu in the above equation, we get at low frequencies, Planck's radiation formula becomes equal to Rayleigh Jeans formula. Let's substitute here, we get 8 pi kt nu square d nu by c cube. This is Rayleigh Jeans formula. So, at low frequencies, the Planck's radiation law obey the Rayleigh Jeans formula. On differentiating Planck's expression and applying a usual test for the maximum we obtain Wein's displacement law, and on integrating the expression over all values of lambda from 0 to infinity, the value of the total radiation obtained is found to be proportional to t raised to 4, which is Stefan's fourth power law. Thus, Planck's law is a better representation of a thermal radiation. So, let me conclude the session. Today we discuss the chemical potential for an open system, then some of the applications of thermodynamics such as black body radiation, black body spectrum, then ultraviolet catastrophe, Rayleigh Jeans formula, then we discuss the famous Stefan's Boltzmann law, then Wein's displacement law, and finally we arrive a general radiation formula, that is Planck's radiation formula. So, hope you have enjoyed the session. See you next time. Until then, goodbye.